Chapter 14, Section 1, Work and Power. The definition for work is that it is the product of some force applied over a specific distance. It requires motion in order for work to actually be done. So if there is no distance an object is being moved over, then there is no work being done. So for example, if you have a boulder and you are trying to move the boulder but it does not move, no work has been done on the boulder. So you need a force applied over a distance for this to work. So no movement equals no force, or equals no work. It depends on direction. So any part of the force that does not act in the direction of motion does not do any work on an object. So for example, friction is a force that opposes motion. So friction does no work on an object. You can calculate work with the following formula. Work equals force multiplied by the distance. So W equals FD. And we're going to measure work by using the unit joule, Joule. And we're going to represent that with a capital J when we look at our examples. So here is your first example. I want to know how much work does a 25 Newton force do to lift a potted plant from the floor to a shelf that's 1.5 meters high. So here's our formula. W equals FD. F is 25 newtons. D is 1.5. So when you plug that in, you should get about 37.5 joules. So 37.5 J. Now I do have a couple of practice problems. How much work is done when you have a 10 Newton force that moves an object 2.5 meters? So W equals FD. We have 10 newtons and we have 2.5. Multiply those and you'll get your answer. We'll go over that in class. Power is something else that we need to look at. It's the rate of doing work. So anytime I say that there's a rate of doing something, that means that there is a time involved. So we do have a formula for power. So if we do work at a faster rate, so if we do the same amount of work in less time, it requires more power or more energy. If we want to increase the amount of power we have, we can either increase the amount of work done in a specific amount of time, or we can do the same amount of work in less time. So calculating power. Power equals work divided by time, or W over T. We can also write that as FD divided by T. So right here, I'm just taking in the formula for work and plugging it in. You may have to do this in some of your examples that we do in class. So W divided by T equals the same thing as force multiplied by distance, then divided by time. And again, you see parentheses here. Those are important if you plug this into the calculator so that you can actually get the correct answer. Power is measured in watts, so capital W. Here's the thing. Do not confuse the units for power with the representation or the variable for work. So in your formula, it's capital W for work, but in your units, it's capital W for power. Here's an example. You exert a vertical force of 72 newtons to lift a box to a height of 1 meter in 2 seconds. How much power is used to lift the box? So here, I'm not giving you the work. I want you to calculate that. I want you to find that first. So power should equal your work, or force times distance, divided by T. So let's go ahead and plug in 72 times 1, get that number, and then divide by 2. So what essentially is 72 divided by 2? You should get roughly 36 watts, or 36 W. Here's a practice problem. You lift a large bag of flour from the floor to the counter. If you do 100 joules of work in 2 seconds, how much power do you use to lift the bag of flour? So joules, that's our work. That goes in the numerator. Time, that's in seconds. That goes in the denominator. So 100 divided by 2. and you should get 50 watts. Now, last thing is horsepower. And horsepower is a very common term, especially if you've looked at horsepower for cars, for lawnmowers, that type of thing. The guy that came up with horsepower, it was James Watt. So he actually gave us our units for power. He lived from 1736 to 1819. He was Scottish. And what he wanted to do was come up with a way to compare power in watts, as far as electricity goes, to a commonly used source of power so that common people would understand just how much watts or how much power something was using. So he came up with the idea to use horses. Back in 1700s, or the mid 1700s, early 1800s, everything that they used was horsepower. They would use horses to pull buggies, horses to plow their fields. So they had this idea of how much power a decent horse would have. So that's what he compared it to. So his statement was that 1 horsepower is the same as saying 746 watts. So keep that in mind. That'll be on your test. And that's it for today.